Greetings, everybody. Learning as a hobby here. I want to finish up chapter 1 today in John Stillwell's Mathematics and its History. Uh, I've already posted videos for sections 1.1 up until 1.3, I think. So today we're going to finish the rest of the chapter 1, which is starts in 1.4 and ends in 1.6. And then there's a little passage about the like a tiny little biography about Pythagoras of Samos that I'll read to you guys at the end. So let me bring up the notes that I took, and I think because these are kind of short, I think I'll do the exercise sets in this video in addition to the section summaries, so that because like I said, it's short, so we could get through all of that in one video. So let me bring up my notes to start with. All right, so we'll start in section 1.4, obviously Mathematics and History by John Stillwell. So section 1.4 is really short. It's just about some visual proofs about the Pythagorean theorem. And I'll show you the picture that he has in the book of one example that he gives. There's many examples of visual proofs of the Pythagorean theorem. And in antiquity, geometric proofs, a lot of them were based on visual being able to visualize these things, right? As opposed to numbers, because or like arithmetical concepts, because the Greeks separated geometry from arithmetic for reasons that we'll see in a second. So let me just show you the proof that he has in the book so you can see it. If I can get the toolbar to go away. Okay. That's not what I wanted. I can't reach it here. This toolbar's in the way. Oh, there it goes. Okay. Whoops. Sorry. Having some technical difficulties here. So this is the visual proof that he has in the book. So here you can see the shaded square over here in this picture here. The area of that, or dimensions of that shaded square are the length of the hypotenuse of these four right triangles here. So each of these triangles here has the same area. They're the same dimension. So this is a square. The area here is equal to the square of the hypotenuse on that right triangle. All right, but if you rearrange things, then notice that you get. So this is the same right triangle that I have drawn on the right-hand side. But if you flip this one over, and you flip this one over like this, I guess, and then flip it around, then you get this picture here. So notice that the area of the shaded square here is actually equal to the area of the square, the sum of the areas of the squares on the sides of the triangle. So that's a visual proof of the Pythagorean theorem, right? This area here plus this area here gives you this area here. So it's a visual proof of the Pythagorean theorem. And there, like I said, there's many others. This is just one of them. Does he say in the book where this one comes from? I think he says this one is in Heath or something. Where does he say that? Yeah, here, figure 1.7 given by Heath, Heath's edition of Euclid's Elements, which I've talked about in a previous video in this series. So that's you could see this visual proof there. Let's go. So like I said, this is a short section. So let's actually go to the exercise sets, because that's basically it. uh, and the first exercise, like I said, this is about visualizing, proofs of the Pythagorean theorem. So it's too hard to draw this tessellation here, so I figured I just used the one from the book here. So the first exercise says this: a way to see the Pythagorean theorem in a tiled floor was suggested by Magnus, 1974. He has a reference to the book in his bibliography, and it is shown by figure 1.8. The dotted squares are not tiles, they are a hint. So, and then he wants you to explain why. So what has this figure to do with the Pythagorean theorem? Let me do this just because, like I said, this is a visual proof. So see if you can figure that out. Pause the screen and see if you can figure out how you can see the Pythagorean theorem in this picture, and then I'll make it obvious if you don't see it. So pause the screen and I'll show you in a minute. Okay, so let's hopefully you guys were able to see that. Again, that's the whole idea, is it's a visual proof, right? So let me show you the idea. So notice this, let me actually do this one in red here. Notice this triangle. Oops. So this triangle, this is a right triangle here. So that right triangle, notice the hypotenuse of that triangle is the dimension of a square. It gives you the dimension of the dotted square. Let me just outline that in a different color just to make it obvious. So this the square with the dotted outline has sides equal to the length of the hypotenuse of that red triangle. And notice that if I highlight certain parts of this inside the square here, so the red triangle that I have here plus this part here, and when I say plus, I mean the area of it, plus this part here, just fill it in to make it maybe a little bit more obvious. Right, that plus the area here. If you notice, is the area of the bigger square in the tessellation. Right, this area is equal to the area that I have shaded in the green square, and this part, the area in the remaining pieces, so this part here plus this part here, notice that that area is equal to the area of the smaller square. Okay, and notice that the side of the blue square is one of the dimensions of this right triangle here. Maybe I'll outline it in black. So here, notice that this side is the dimension of this square, and this side is the dimension of the red square, and the hypotenuse of that triangle is the area. Sorry, it's the dimension of the green square. So that's the visual proof. So hopefully you were able to see that. So that's section 1.4. That's really all it contains. Let me go back to my notes so you can see over here. Okay, so that's 1.4. 1.5, we talk about here. He talks about what the problems were in ancient Greek mathematics. One of the major stumbling blocks was there's several, but one of them was the existence of irrational numbers or incommensurable, like what they call incommensurable lengths. So the Pythagoreans are credited with discovering incommensurable lengths by their study of the Pythagorean theorem. In other words, these lengths cannot be expressed as whole number ratios of a unit length. So in other words, they're not ratios of integers, so they're not rational. Then that means that these ratios are irrational. And that was a problem for the Pythagoreans in particular, but for the ancient Greek mathematicians in general, because they built their theory around the fact that everything could be expressed in mathematics. By mathematics, they meant rational numbers. So this discovery caused much consternation among the Pythagoreans and the Greek mathematicians in general, because they had problems with infinities and things like that, and there wasn't really a well-defined meaning given to these incommensurable lengths, or these irrational numbers. But they did develop a very sophisticated theory of working with them. So in fact, this leads to the separation between number and geometry, so they separated geometry and arithmetic into two different things. So geometry had this sort of, in their minds, pathological property of having incommensurable lengths, and arithmetic was about numbers, and like I said, by numbers they meant rational numbers. So in fact, this leads to the separation between number and geometry. This separation made certain relations among the two branches unavailable to the ancients, so they didn't have access to certain concepts that we don't have today, which held mathematics back for a long time. And just to illustrate how one way you could see that there are incommensurable lengths is to look at the unit square. The diagonal on the unit square has length square root 2 by the Pythagorean theorem, right? 1 squared plus 1 squared equals x squared in this picture, which means that x squared is equal to 2, or in other words, x is the square root of 2. Unfortunately, square root 2 is not rational. And we'll prove that here. But before I actually prove it, we do need a lemma, which I'll prove first. So the lemma is that if a squared is even, then a is even. In fact, you could weaken this a little bit. This is if and only if. So it actually goes both ways. And there's a similar lemma for odd numbers. So if a squared is odd, then if and only if a is odd. Before we consider the proof that square root 2 is irrational, we first need this lemma. So here I proved this by the contrapositive. Let a be odd. So the contrapositive of a, in case you don't remember from when you learned logic, this is called a conditional statement. This is read if p then q. The contrapositive statement of this is not q. If not q, then not p. This is called the contrapositive. And these two statements are logically equivalent, meaning that for any truth value assignment to the atomic statements P and Q, they both take on the same truth values. For both of them have the same truth table. So they're logically equivalent. So if you prove the contrapositive, then you've proven the conditional itself. So that's what I'm using here, a proof by contrapositive. So here, not P would be let A be odd. So let A be odd, then what that means is there exists a natural number n in Z, such that A is 2n plus 1. And then if you consider A squared, that's the same thing as 2n plus 1 squared. If you multiply that out, you get 4n squared plus 4n plus 1, which is the same thing as 2 times 2n squared plus 2n, in parentheses, plus 1. Uh, and 2n squared plus 2n is also an integer, because the integers are closed under multiplication and addition. Therefore, a squared is of the form of an odd number, so it's odd. So using that that lemma, we can prove that square root 2 is irrational. And and he says here, which this book I don't have, so I can't look it up, but this is a well-known proof anyway. A version of the proof that I'm going to show you in a second can be found in Aristotle's Prior Analytics, which again, like I said, I don't have a copy of Aristotle's Prior Analytics, and I'm not very read in Aristotle's oeuvre, I guess. I have read his Politics, but I haven't read any of his other books, like on mechanics or physics or whatever. But apparently this proof is in there. However, every mathematics major knows this proof because it's shown, it's a part of history and it's shown to you in proof classes. So, if you might have seen this proof before, is what I'm trying to get at. So anyway, here's the proposition: square root 2 is not rational. All right. So here here it is. We do this by a proof by contradiction. Assume there exists integers m and n, where n is not 0, and m and n have no common factors, and that square root 2 is equal to m over n. So m and n having no common factors means that m over n is in reduced form. That fraction is in reduced form. All right. Then if you square both sides, that means that 2 is equal to m squared over n squared. And multiplying both sides by n squared gives you m squared is 2n squared. But by the previous lemma, that means that m squared is even, which means m is even. So there exists a q in Z such that m is 2q. And m squared then would be 2q squared, or in other words, 4q squared. And that's equal to 2n squared from above, which means that 2q squared is equal to n squared. But that means that n squared is even. And by the previous lemma, that means n is even. And this contradicts the fact that m and n have no common factors, so this can't possibly be the case. So this shows that there are no integers m and n whose ratio gives you the square root of 2. So square root 2 is the diagonal of the unit square is incommensurable, or in other words, square root 2 is irrational, right? And like I said, this led to profound worry in the ancient Greeks who studied mathematics. The Greek separation between number and space led to ingenious techniques for precise handling of arbitrary lengths in terms of rationals, called the theory of proportions, and the method of exhaustion, which I believe the theory of proportions was, correct me if I'm wrong, I think it was Eudoxus who was responsible for that theory, and the method of exhaustion was used by Archimedes. He used it. We'll look at that in later, things. For example, the method exhaustion is explored in Apostol's 2-volume calculus book. It's also in what's his name? Let's drawing a blank. His book, A Radical Approach to Real Analysis. I can't. His name starts with a B. I can't think of it right now. But he goes into detail about the method of exhaustion too. So in the 19th century, Dedekind realized that these methods provided an arithmetical interpretation of irrational quantities. It was then possible for Hilbert to reconcile arithmetic with geometry. And again, Dedekind's study of the set of real numbers in particular, he found a definition for which gives meaning to irrational numbers, and they're called Dedekind cuts. That's something that we'll explore. I think even in Spivak, he does a construction of the real numbers in an appendix. So we'll do that eventually in Spivak. He does a construction of the real numbers using Dedekind cuts. So that's something that we'll actually go through together at some point in the future in Spivak. So this gives Dedekind gave an actual valid foundation to the real numbers, and that led to the reconciliation of arithmetic with geometry. All right, so this is, before we go to section 1.6, let's do the exercises from this section 1.5. I forgot to do this exercise also from 1.4. Let's actually do this first, because I just realized I skipped this. So this is just going back to 1.4 real quick. Euclid's first proof of the Pythagorean theorem in book 1 of the Elements is also based on area. It depends only on the fact that triangles in the same base and height with the same base and height have equal area, though it involves a rather complicated figure. In book 6, proposition 31, he gives another proof based on similar triangles, which I have drawn down here. This is figure 1.9. And he, in question 2 in section 1.4, he says, show that the three triangles in figure 1.9 are similar and hence prove that the Pythagorean theorem, prove the Pythagorean theorem by equating ratios of corresponding sides. So here's the picture. Let me make it a little bit bigger so you can see the labels, because they do look a bit small. So this is our triangle. So what he's saying is this triangle here is similar to this, is similar to this triangle. And they're both similar to the large triangle. Maybe I'll do it, in purple or orange, maybe. And both of those are similar to to this larger triangle here. All right. And just so we have names for everything, this is how we're labeling the sides. All right, so from the picture, here call the altitude H, and side C is C1 plus C2, just so you can see in the picture. So side C is C1 plus C2, and H is the altitude. Right, then angle AH plus angle HB equals angle AB. Actually, I'm gonna have to make this smaller so I can fit it all in one. Whoops, in one. Screen here. Okay. The angle AH plus angle HB equals angle AB. So let's see, AH and HB. So AH is this angle, and HB is this angle here. So this angle here is equal to angle AB. Triangle ABC is similar to triangle C1HA, since angle AC1 equals angle AC. So, in other words, they're sharing an angle here. So triangle ABC is the big one, right? ABC is the big triangle. And I say here, triangle ABC similar to triangle C1HA. That's this one here. That's this triangle. We're saying is similar to this triangle. since angle AC1 equals angle AC. So in other words, if you notice over here, sorry, I have to keep going back and forth, but this angle is shared by both this triangle and this triangle, right? And these are both right-angled triangles. So two of their angles match, therefore the third angle, therefore the third angle also has to match, which means that they're similar triangles. All right, so all three of their angles are the same. Similarly, the triangle ABC is similar to triangle HC2B, since they both share angle BC2. So in other words, this triangle and this triangle share this angle, and they're both right triangles, so that all three of their angles have to be the same, therefore they're similar triangles. And they're both right triangles, so all three of their angles are the same, so all three triangles are similar by transitivity. Right, so that means that A over C is equal to C1 over A, and B over C is equal to C2 over B. That's just the property of similar triangles. Therefore, A squared is CC1, and B squared is CC2, and A squared plus B squared is C times C1 plus C times C2, and then if you factor out the C, you get C times C1 plus C2, which is C squared. Therefore, A squared plus B squared is C squared. All right, so that's the proof of that question. All right, going to section 1.5, which is the one we just went over. The crucial step in the proof that square root 2 is irrational is showing that m squared even implies m even, or equivalently that m odd implies m squared odd. It is worth taking a closer look at why this is true. All right, so here's the first question in section 1.5. Writing an arbitrary odd number m in the form 2q plus 1 for some integer q, show that m squared is also has the form 2r plus 1, which shows that m squared is also odd. We've actually, this is basically the contrapositive of what we did in the section, I mean. So here, let m be odd, then there exists an integer q such that m is 2q plus 1. So it's the same proof, so I won't really, go over it again. Question 1.5.2, show that the square of 2q plus 1 is in fact of the form 4s plus 1, and hence explain why every integer square leaves remainder 0 or 1 on division by 4. So here, if you square 2q plus 1, you get 4 times an integer plus 1 from you can see that from up here. Right, if you square this, you get something that looks like this, and you can factor out the 4. So 2q plus 1 squared. So you get something that looks like this, and q squared plus q is an integer, so I'm calling it r. So 2q plus 1 squared gives you something of the form 4r plus 1 for some integer r by the solution of the previous question. Noting also that 2q squared equals 4q squared shows that the square of any integer has remainder 0 if the integer is even. A remainder of 0, I mean, when you divide by 4, and has remainder 1 when the integer is odd upon division by 4. Right, so that's the solution. And I think the next question is for 1.6. So let's actually go to the section 1.6. Okay, so in section 1.6, now that Dedekind has given a foundation for the real numbers, now we can we have a meaningful notion of numerical measure for lengths, and that gives us analytic geometry, basically. So the numerical interpretation of irrationals gave each length a numerical measure. This allows for the formulation of analytic geometry. So we're all familiar with this picture here. If you have a point in the plane, x, y, that is, the coordinates are given in terms of the lengths of a horizontal distance on the horizontal axis and a length on the vertical axis. So here, length OP is what we call the x coordinate, and length OQ is what we call the y coordinate of the point. And with this formulation, geometric properties of x, y are then reflected by arithmetical relations between x and y. Analytic geometry, what we're all nowadays, this is like the way that people think about things. So this should be pretty familiar to you. Okay, how do coordinates give a precise meaning to the basic geometric notion of distance? Right, so if we define the distance from point P to another point along the same perpendicular to an axis to be the difference of the coordinates. So in other words, if you look at the picture here, length RP, which is this length here, has coordinates y1 minus y2 in absolute value because they may be inverted or whatever. So you want the length to be positive, so take the absolute value because sometimes the difference of the coordinates might be negative. And the length QR, which is this length here, again is given by x1 minus x2 in absolute value. All right, so with those definitions for the lengths in the vertical and horizontal directions, then the Pythagorean theorem says that length QR squared plus length RP squared is length QP squared. Or in other words, x1 minus x2 squared plus y1 minus y2 squared is length QP squared. Length QP is the hypotenuse of that right triangle in the picture that I drew. Therefore, the distance from Q to P is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. So in other words, the Pythagorean theorem is what gives the correspondence between Euclidean geometry and arithmetic. So since P and Q were arbitrary, this formula gives the numerical distance between any 2 points in the plane. Right, Hilbert realized that taking this as the definition of distance says that geometry is arithmetic. In other words, all geometric facts become facts about numbers. Okay, and the Pythagorean theorem is precisely what is needed to interpret arithmetical facts as geometry. So we can go back and forth between geometry and number. So one branch informs the other and vice versa. Okay, and then there's just two last questions in chapter 1, and then I want to read you the little biographical article that he has about Pythagoras. All right, so here are the questions in section 1.6. Most mathematicians these days are familiar with coordinates, more familiar with coordinates than traditional geometry, yet certain theorems of analytic geometry are seldom proved because they seem visually obvious. A good example is what Hilbert in 1899 calls additivity of segments. So if A, B, and C are points in that order on a line, then AB plus BC equals AC, something that should be geometrically obvious by looking at a picture. Here he wants us to show that analytically you get the same thing by using the distance formula. So this is question 1.6.1. By suitably naming the coordinates for A, B, and C, show that the equation AB plus BC equals AC is equivalent to this in terms of the numerical distances or the numerical lengths, where x1, y2 is equal to y1, x2. And he gives a hint here. He says it's convenient to let B be the origin. So that's what I did in the picture here. Now you get to choose your coordinate system, so you can choose whatever you want to be the origin. So here, if we choose B to be the origin, and we look at these 3 collinear points, A, B, C, that go in this direction. So A first, then B second, then C third. A has coordinates. A has coordinates negative x1, negative y1. B has coordinates 0, 0 because it's the origin, and C has coordinates x2, y2. And we're assuming that A, B, and C are collinear, then that means that they lie along the same line, so they have the same slope, right? So that means that negative y1 minus 0 over negative x1 minus 0 gives you y1 over x1, and that's equal to y2 minus 0 over x2 minus 0, which simplifies to y2 over x2, or in other words, y1 over x1 equals y2 over x2, and just cross multiplying gives you the relation that we want. So that implies that x1 y2 equals y1 x2. Okay, and then if you look at the lengths based on the definitions, you see that it matches. So length AB is given by the formula that we're taking as a definition for the numerical length. Length AB is square root in parentheses negative x1 minus 0 squared plus in parentheses negative y1 minus 0 squared, which simplifies to give you square root x 1 squared plus y1 squared. And length BC, same thing. You get square root x2 squared plus y2 squared. Just, use the same formula. And also from the picture and the definition, you can see that length AC is equal to, let me draw the picture so you can see, that's equal to this length here, which is equal to length x2 minus length x1, which is x2 plus x1. And then same thing for the y's, right? If you add the y's together, you get the sum y2 plus y1, right? So the length of AC is equal to square root x2 squared, x2 plus x1 squared plus y2 plus y1 squared. Therefore, if AB plus BC equals AC, you get the same exact correspondence between the numerical lengths, so that they give you the same thing, right? So that they're equivalent. Except one is formulated in terms of numbers and the other is formulated in terms of geometry. All right, and then the last question in 1.6, prove that star is the formula that we just looked at here. Prove star by proving an equivalent rational equation obtained by squaring twice and using x1 y2 equals y1 x2. So here, what you do is you sort of work backwards to see what you want, and then go forward for the proof. So here, squaring the relation that you want gives you what you want going this way, and then for the proof we just go this way. So 2x1 x2 y1 y2. If you use the fact that they gave us, that the points are collinear, and the rational equation that we derive by going backwards. So you get that 2x here. It's you don't have. Sorry, I'm getting tongue-tied here. This is obviously true, what I have written here first, just by the arithmetic. So and the fact that they gave us. So 2x1 x2 y1 y2 is equal to 2 times x1 y2 squared, which is equal to x1 y2 squared plus x1 y2 squared, right? Because you just split it up into the sum. And by the fact that the points are collinear, that's equal to x1 y2 squared plus y1 x2 squared, and that's equivalent to saying that x1. So here, if you add this to both sides of the equation here, you get on the left hand side x1 x2 squared plus 2x1 x2 y1 y2 plus y1 y2 squared is equal to x1 x2 squared plus x1 squared y2 squared plus x2 squared y1 squared plus y1 y2 squared. And then if you notice, the left hand side over here factors into this square of this binomial, and on the right hand side this factors into the product of these two binomials. All right, and then you could take the square root of both sides, and that gives you this equation here, which should look familiar. We actually looked at this. Well, we looked at the inequality in Spivak, but here we have actually equality. But we looked at something that looks similar to this, but with an inequality sign in Spivak. So x1 x2 plus y1 y2 equals square root x1 squared plus y1 squared times square root x2 squared plus y2 squared. And from there, if you square both sides, you get the next line. Okay, and from there, what did I do? Going from did I square both sides? I squared both sides. X1, Y1. Sorry, let me just see. I did this a long time ago. So X1 squared. I see. So here, this part here is this, the square of this expression here. And then, yeah, here, this is the square of that expression. And if you notice, if you take the square root of that expression there, then you get the relation star. Right? So that shows that that relationship is true for coordinates that satisfy, this condition, which is equivalent to the points being collinear. All right, and that's the end of the exercises in chapter 1. He does have a little note here. It should be stressed that Hilbert is concerned not only with defining geometric concepts in terms of coordinates, but also with the reverse process, setting up geometric assumptions from which coordinates may be rigorously derived. There's more about this in section 2.1 and 20.7. Okay, I think that's it for the exercises. Let me stop my screen share here, and I just want to read you the little article that he has on the biography of Pythagoras at the end of chapter 1, and then we'll be on to chapter 2 at some point soon. All right, let me see. Okay, section 1.7, biographical notes, Pythagoras. Let me just rearrange this so I can read this in the light here. Okay. Very little is known for certain about Pythagoras. Although he figures in many legends, no documents have survived from the period in which he lived. So we have to rely on stories that were passed down for several centuries before being recorded. It appears that he was born on Samos, which is a Greek island near the coast of what is now Turkey, around 580 BCE. He traveled to the nearby mainland town of Miletus, where he learned mathematics from Thales, who lived 624 to 547 BCE, traditionally regarded as the founder of Greek mathematics. Pythagoras also traveled to Egypt and Babylon, where he presumably picked up additional mathematical ideas. Around 540 BCE, he settled in Croton, a Greek colony in what is now southern Italy. There he founded a school whose members later became known as the Pythagoreans. The school's motto was, quote, all is number, unquote, and the Pythagoreans tried to bring the realms of science, religion, and philosophy all under the rule of number. The very word mathematics, which means that which is learned, is said to be a Pythagorean invention. The school imposed a strict code of conduct on its members, which included secrecy, vegetarianism, and a curious taboo on the eating of beans. The code of secrecy meant that mathematical results were considered to be the property of the school, and their individual discoverers were not identified to outsiders. Because of this, we do not know who discovered the Pythagorean theorem, the irrationality of square root 2, or other arithmetical results that will be mentioned in chapter 3. As mentioned in section 1.5, the most notable scientific success of the Pythagorean school was the explanation of musical harmony in terms of whole number ratios. This success inspired the search for a numerical law governing the motion of the planets, a, quote, harmony of the spheres, unquote. Such a law probably cannot be expressed in terms that the Pythagoreans would have accepted. Nevertheless, it seems reasonable to view the expansion of the number concept to meet the needs of geometry, and hence mechanics, as a natural extension of the Pythagorean program. In this sense, Newton's law of gravitation, which we'll study in section 13.3, expresses the harmony that the Pythagoreans were looking for. Even in the strictest sense, Pythagoreanism is very much alive today with the digital computer, digital audios, and digital video, and digital video coding everything at least approximately into sequences of whole numbers. We are closer than ever to a world in which, quote, all is number, unquote. Whether the complete rule of number is wise remains to be seen. It is said that when the Pythagoreans tried to extend their influence into politics, they met with popular resistance. Pythagoras fled, but he was murdered in nearby Metapontum in 497 BCE. All right, and that's the end of chapter 1. So the next chapter is on Greek geometry. So we'll look at the Greek formulation of geometry, as codified by Euclid in his book, The Elements. So I'm looking forward to that. I hope you are too. Let me know what you guys think in the comments. Do give a like and subscribe. And if you'd like to support the channel monetarily, I do have a Patreon page, which you can click on the link to in the banner on the channel. On the Patreon page, you get charged basically $5 a month. And for that $5 a month, you get access to all kinds of other content that I have posted on there. So videos and exercise sets and solutions and stuff to more elementary mathematical topics that that are required to understand the mathematics that we do on the YouTube channel. In fact, I can let you know what we're doing right now. We're in the middle of Blitzer's college algebra book. We are up to chapter 5 right now, and we should finish chapter 5 by next week. So we're going at a pretty nice pace. So if you're rusty on your algebra or any other topics, the next book we'll do is pre-calculus, then we're going to do calculus and so on. So if that sounds interesting to you, please do check out the Patreon page. I thank you guys for watching as always. I hope you're getting as much out of this as I am and enjoying the content. Until the next video, please keep learning, and I'll see you next time.